And okay, I think so. You see my screen, right?
Yes.
Okay. All right. And the full presentation I assume. Okay. All right. Just one thing. Hold on a second. It should be this one. Okay. All right. So welcome you all. Today I'm going to talk about a different topic which we have not addressed in previous seminars or training schools. So for some time in our lab, we have been working with a benchtop MRI system, and we are converting that to a flow imaging system. And today I'm going to talk about how we achieved finally the data analysis part for flow images. And I will be also talking about the flow imaging basics and some engineering challenge that we experienced while we are converting this benchtop MRI to a flow rheometer. So that is basically going to be my topic. Well, and by the way, we also had some experiences on testing this product for different milk samples as well. We looked at the rheological properties of different plant-based milk and compared it with regular whole milk. And we can also test it with different types of emulsions, and I'm going to talk about that in a minute. Okay. Well, so as we know, normally MR imaging is used as targeted for medical applications, but we also know that we can use it for material characterizations, particularly for polymer structure analysis. And another important thing that we can use magnetic resonance imaging, and as a result, the relaxometry that is associated with it, the T1 maps, T2 maps, we can use that to obtain velocity maps, to obtain rheological properties, and visualizing the complex fluid behavior. So, well, before going deep into the MR flow imaging principles, I'm going to give some basic information about the critical role of flow and fluid dynamics in food systems. Well, in food engineering curriculums, we are teaching our students fluid mechanics. Why? Because understanding the fluid flow is important, since in a food processing plant, we have pumps, we have pasteurizers, we have evaporators, which all involves somehow a different form of fluid dynamics. And we have different flow behavior, which also is important because while designing the food processing systems, we have to know the flow behavior of the fluid as well. What does that mean? Well, whether the fluid is following what we call Newtonian, like having a constant viscosity, or whether the fluid has a changing viscosity, or whether the fluid has a yield stress so that it will flow. Okay, let me show this with some more examples. For instance, here you see different types of fluids where we categorize, and I gave the examples particularly for foods. We categorize the fluids Newtonian versus non-Newtonian. Newtonian meaning with changing shear stress and shear rate, we have constant viscosity. Non-Newtonian foods, on the other hand, we have changing viscosity and non-Newtonian fluids can further be classified as shear thinning. So as you apply shear, the viscosity decrease, or shear thickening, as you apply shear, the viscosity increase. Bingham plastic, we have a yield stress for some foods. For instance, here you see a ketchup image. Ketchup has a yield stress. That means that after a certain shear, after a certain force, let's say, it will start to flow. And also we have the viscoelastic behavior, which which gives us some different parameters. So when we talk about viscoelasticity, we usually talk about elastic modulus, the storage modulus or loss modulus, and usually the semi-solid um, foods follow viscoelastic behavior. But for the flow behavior, we are usually talking about these shear thinning, shear thickening behavior, and Bingham plastic is also another category. Well, we have also the mathematical expressions, but which are not as complicated as the relaxometry equations. And these equations are important because once you have a flow of data, you use usually these equations, you fit to these equations to find the viscosity or viscosity related other parameters. For instance, in the case of a Newtonian fluid, yeah, we can directly obtain the viscosity from shear stress, shear rate data. But for a non-Newtonian, we don't have a single viscosity value. We can only calculate viscosity at a certain value. What we can obtain usually is the consistency index and also the consistency index and the flow behavior index, which are the rheological parameters. Or when we have, for instance, yield stress and power law, we need to estimate both the yield stress, the consistency index, and the flow behavior index. So these are like some mathematical expressions that we use while we are dealing with the fluid dynamics. Well, why I'm talking about this? Because later on, once we have a flow MR image, we are going to be utilizing these equations so that we are going to obtain the parameters. We're going to obtain the viscosity, K, or N values. Well, okay, and some other practical applications where fluid dynamics is important in foods. Well, in heat and mass transfer optimization problems, fluid dynamics cover the heat exchanger design, pasteurization process, and we know that pasteurization, for instance, is a very important process for milk. So that is why understanding flow pattern is quite important. For mixing and homogenization, again, the flow behavior is important. For processing line efficiencies, particularly for pump designs, again, the rheological properties, the fluid properties are quite important. Okay, well, flow MRI, in fact, has been studied for a long time, but it is really a shift in rheological characterization. Normally in the courses, we show our students the hypothetical flow images that is seen in a pipe, the velocity profiles in a pipe, but with MRI, in fact, we can really obtain these velocity profiles. And it really provides us real-time information. And if something is happening in your fluid and its rheological properties are changing during the process, flow MRI can really be a good tool. And in fact, how we used this tool was we tested some food colloid solutions in simulated gastric juice, because when you have colloidal solutions entering the gastric juice, which is very low pH, the rheology can drastically change. It can either gel or it can be a thin fluid. And flow MRI can be a great tool to visualize this. So let me show you, for instance, some flow assisted images. Here, these are from some papers from the group which I have done my PhD, where we have a 1 Tesla imaging system and we adapted that system to be a flow MR rheometer, and these images are from there. Here, the flow-assisted MRI measures the velocity profile by tagging the thin fluid slices with RF pulse and tracking their displacement over time. The technique captures the flow behavior across different rheological regimes, from Newtonian to complex non-Newtonian fluids with yield stress behavior. For instance, here, that's a very important, that's a very good example for such a fluid. So here we have a velocity profile, which is getting like flat at the maximum position. Normally we expect for a Newtonian fluid to have a complete parabolic profile. Here we have like a flattening. And in fact, this flattening means we have a yield stress for that fluid. And yield stress of that fluid can directly be calculated with some analysis. Okay, so we can obtain direct flow field mapping. We can obtain some wall slip conditions, which I'm also going to show some examples. And as we know, when we are describing MRI, we say that it's non-destructive. So compared to a conventional rheological analysis, so you just let the flow in the pipe and you image it and you obtain the rheological information. So you don't need to destroy that sample by using the cone and plate or the Bobot cup apparatus in a rheology instrument. Well, there are different flow imaging techniques, inflow outflow techniques, time of flight methods, phase encoding technique, and usually, and the one that we have used is the phase encoding technique. Each technique offers unique advantages depending on specific application and the required resolution. Phase encoding ones provides the highest accuracy for quantitative velocity measurement, since we want to find the rheological parameters, the quantitative parameters. We wanted to utilize this phase encoding system. Okay, so this is in fact the simulation of our MRI system that we have set up in our lab. So let me also show this animation. Okay, so here the fluid is pumped from a reservoir, and then you see on the center our magnet, and the flow is there is a certain area in the RF coil that we are imaging. At the entrance and exit of the system, we have pressure transducers, flow meters, pressure and temperature transducers, and also we have flow meter to control the also flow. So this we are extracting the velocity profile as you see in the image, and with time it is also possible that a fluid which starts with a completely Newtonian profile with no yield stress can switch to a fluid with a yield stress, for instance, if the processing conditions are different. And in this case, what we have done here is we have a fluid initially, and then we started to add to this reservoir some gastric juice, which is at pH 1, and the pH decreased significantly, so the polymers changed, and as a result, the flow behavior changed. And we can easily monitor that through this system. this system that we utilize is pure device MRI system. It is a 0.5 Tesla MRI system that can that has like a special design to integrate this flow apparatus. Like both ends are open. I'm going to show the system also later on. Okay, oops. Well, sorry. Oops. Okay. Well, here first, I also want to mention about some other engineering design issues that you need to be careful about while transforming an MRI system to a flow MRI system. And by the way, all this engineering design of the previous flow system, we made all the calculations by using these fluid dynamics principles. Well, first of all, as we all know, depending on the velocity, we have the Reynolds number for the fluids. And in order to do flow MR imaging, we need to be on the laminar flow range. So, and usually we want the Reynolds number even below that 100 so that we will have good accurate measurements. And we also need to be sure about the entrance length, because once fluid enters the pipe, it will not attain its parabolic flow instantaneously. So you need to ensure that you have some entrance length, and this entrance length should be before the RF coil so that you will have this nice flow image. So you should have an idea about the fluid properties, the density, the viscosity, and we use the Bernoulli equation to do the necessary engineering calculations. And of course, while making the design, we made the design by using water with a simple, since with water, the system will be like at the maximum length, and the viscosity of water is smaller compared to the most of the other foods. So that is why, I mean, we made our design calculations with respect to water by using the Bernoulli equation. Well, the schematic representation of our system is shown here. Well, whenever you are doing a flow imaging system, the thing is you are working at slow rates, low flow rates. And in order to work with low flow rates, usually you use a peristaltic pump. But when you use a peristaltic pump in for imaging purposes, well, peristaltic pump usually have a pulse. Okay, and here you see like how the pulses of the peristaltic pulse. So if you integrate a peristaltic pump to your flow system and let the flow directly be taken from the pump, in such a case, you will experience significant noise, image blurring due to the pulsation artifacts, and there will be a flow instability, there will be pressure calculation errors. So that is why you will not be able to have a good image by using a peristaltic pump. However, you may, by the way, for some flow imaging systems, I know that rather than peristaltic pumps, for instance, syringe pumps are being utilized. Syringe pumps are much easier to utilize. However, the syringe pumps usually suffer from the problem that you put the fluid from the beginning and then you cannot later on change the processing condition, change the fluid environment. So, for instance, here we have the reservoir where we can easily add gastric juice and let the fluid conditions to change so that it will have another rheological behavior. But without that, we cannot do that in a syringe pump. It was a challenge. So that is why, and for the slow flow rates, we wanted to use a peristaltic pump. So that is like one of the first engineering challenge that we experienced. Later on, we put a pulsation dampener. Well, pulsation dampeners can be considered like an apparatus. Well, it absorbs the excess fluid during pressure peaks, releases store fluid during pressure valleys, and the fill gaps, and this fluid smoothing will enable to fill the gaps caused by the peristaltic pulsation. This can be really a strategy to overcome the problem of the peristaltic pump in flow imaging. However, we also suffered some problems when we had high viscosity samples and when you have, for instance, a fluid that like a xanthan solution. So this dampener's pressure should also be tolerable, and we were not able to have the effectiveness we wanted. I mean, of course, we could have let some other designs to be integrated, but we want to select another solution. So that is why what we did was we designed a gravity-driven system. So what we have done is rather than the reservoir being pumping the fluid from the bottom, we put a reservoir also to the top. And in such a case, we have the fluids leaving the system, and we use pump transverse fluid to elevate the reservoir with constant level wall control during the measurements. And here we achieved excellent velocity profile. So here you see, for instance, this is a perfect velocity profile, the desired parabolic profile that you expect with a flow image system. And however, when you do such a system, what we have experienced is we experience some pressure measurement issues. We have high fluctuation. The gravity-driven problem eliminated the pulsation issues, but revealed the need for higher pressure differences to improve measurement accuracy. So that is why later on we also did some piping adjustment. We extended transducer distance and reduced the pumping diameter. However, in such a case, the hydrostatic pressure increases at the bottom while dynamic pressure increases at the top due to the frictional losses. So we experience another fluid dynamic problems, and the overall delta P decreased, which is also not the case that we were expecting. So that is why we again did some other calculations, and finally we also realized that the ADC sampling frequency of the pressure transducer was also important. Pressure measurement on the transducer exhibited the zigzag fluctuations that initially appeared to be transducer error. In fact, we figured out that the sampling frequency mismatch between the transducer and the measurement intervals was the reason. So that is why we also arranged that with some MATLAB optimization. And finally, we were able to have with 8mm diameter tubing, extended transducer separation, vertically downward orientation, with gravity-fed reservoir system, we were able to have a very nice flow MR image with fluctuations that are minimal. And so if our secondees in NMR Improve are going to come to our lab, so they will have the chance also to test the samples for different dairy formulations. Okay, and here you see our system. Well, this is like the fully integrated, so it looks like simplistic. So this is our MR system. We have our pumps all here. We have our reservoir. So these are all Teflon pipes. And here you see we have a transducer, another transducer here, and with our MATLAB based interface, we are able to obtain this nice velocity profiles. Well, we filled the complete tubing system first with test fluid, inspect the pressure sensors for some bubble contamination. We do the offset calibration, and then we do the magnet calibration, and we need to do some inputs, parameter inputs. Well, for the pulse sequence, we are using PGC, pulse gradient spinnacle, which is also used for the self-diffusion coefficient measurements. And in fact, this is like the gold standard for velocity imaging, which applies RF pulses with special gradients to encode the motion. And the phase shifts are proportional to spin displacement, which enable quantitative velocity measurements across the flow profile. Proper shear rate range, velocity encoding steps, and averaging parameters ensure high quality, artifact-free images. And here, the critical requirements are laminar, pulsation-free flow, accurate shear rate estimation. Incorrect parameters will result in wrapping artifacts and degraded image quality. Well, of course, repetition time, the phase encoding steps, and the number of average excitations are important parameters that will affect also our duration for imaging. So we need to optimize these parameters so that we will have a desired good quality image. Well, if you do not set the parameters properly, we may have aliasing artifacts, or for instance, with not sufficient repetition time or with not sufficient excitations, the signal to noise ratio may suffer significantly. For instance, here we see some low SNR images, or here we see some aliasing. Again, these are due to incorrect parameter settings. Well, here we are using a MATLAB-based analysis software which process raw MR data to extract quantitative velocity profile. The workflow utilizes image reconstruction, phase unwrapping, velocity calculation, rheological parameter extraction. Here I show you one Newtonian fluid with no yield stress and one Newtonian fluid with yield stress. Well, velocity image is in fact obtained through a quadratic equation, and then we obtain shear rate by differentiation of the velocity profile. These are usually the approach that we utilize, that are utilized in literature. And this equation, the shear stress, comes from this Hagen-Poiseuille law. Which shows shear stress depends on the pressure difference and also the pipe length. And what information can we obtain? Well, symmetric parabolic profiles are usually indicating classic Newtonian fluid behavior with predictable velocity distribution. We have plug flow phenomena, the yield stress usually exhibiting flat velocity profiles. If you have asymmetric flow patterns, for instance, in some of our samples, once we introduce gastric juice, the hydrocolloids in fact precipitated, forming some heterogeneous particles. In such a case, you see asymmetric flow profile. So this is also, this information can also be obtained from a flow image. So flow behavior change, slip boundary analysis, strain rate heterogeneity. So all these can be used as advanced flow characterization tools from the MR images. Well, of course, when you do such a system, the important thing is you need to compare your results with the conventional rheology results so that you will be sure whether the results are correlated. So that is why, for instance, here for the samples that we have tested through flow image, we also did their conventional rheological analysis for different types of fluids. So for Newtonian and non-Newtonian. And the flow MR and the conventional rheology results showed correlations greater than 0.90. So that means this flow imaging is capable of characterizing or obtaining the rheological parameters. Well, in the literature, as I said, there are flow rheometers and there are even dedicated MR-based flow MR systems as well. I remember one company was producing that. But here the important point is the system should let you to change the sample so that you will be monitoring the changes on the rheological fluids, rheological properties of your sample. The idea of this project was, in fact, we were trying to create some emulsions which will gel in your stomach and which will feel you full for a long time. So it will like increase your satiety when you drink that emulsion because it will gel and the gel will flow at a slower rate to your intestine so you will not be hungry very quickly. So that was the idea. And we were able to show that this rheological change for some of the emulsions, some of the hydrocolloid combinations that we tested, in fact, experienced that flow behavior change, and we were able to quantify it through our flow MR system. So that's all I want to talk about. Thank you, and I can get your questions if you have.
Thank you, Mecit.
Thank you.
Thank you.
It seems that we have a question from Dennis.
Yeah,
Yes.
hello. Wait, where's my camera? Ah, right, it's closed. I'm also here with Stella. Thank you for presentation. I just have one small question. Could you show again the color maps for the profiles? Because I didn't quite understand I didn't see the color bars, so that I didn't understand what it means. I understand it in terms of velocity versus radius, but when there is additional color, I don't know what this means.
Okay, let me hold on a second. Let me share it again. So sorry. Okay, so I think here, for instance, you are asking what this image, like what the signal intensity, right?
Basically, like what does color encode in this image, in this plot? Yeah.
Okay, well, the color code. Yeah, well, I haven't thought about it. Well, we are taking the signal average, and I think since it should be denoting the maximum velocity,
Mhm.
certain velocity range. That is what I believe. I don't know, Esma, you are here. Are you listening us?
Yes, hocam, I was listening to you. The colors, the yellow colors represents the maximum velocity that we have. The others, the velocity is going down. At the
Yeah.
walls is the wall slip. It means that no velocity at that parts, or the
Mhm.
minimum velocity.
Okay.
Okay, and the horizontal axis is
Horizontal axis is the velocity, actually. Yeah.
okay, yeah, it's a little bit confusing, but yeah, thank you.
Okay.
More questions? Mecit, who produces this equipment and how much does it cost?
It is I mean, we bought it like 3-4 years ago, I guess. Pure Device, a small company in Germany.
Okay.
And at that time, I think it was like without the external gradient, it was 58K. Plus the gradient, it was extra 10K. So around 70K. But this system, like we built the flow system completely with ourselves.
Yes.
Okay. Mecit?
Yes.
Mecit?
Do you hear?
Sorry, I had my video closed. So thank you. Nice presentation. I'm just wondering, which are the practical application you can foresee for this study? You are right. I've seen many study to measure flow through NMR, MRI. So apart the application you explain, which is really fascinating, what else do you believe can be an application for this?
Well, first of all, it is important that, for instance, in food processing, like we apply heat treatment to many like liquid foods, and heating may change the rheological properties significantly. So, for instance, for a sauce, if heating is increasing the viscosity, it may not be in the desired range. So if you can monitor it right away, so that will be like a good tool. I know that in US, a tomato company was using it for tomato paste, tomato sauce to monitor their rheological properties.
Okay.
That is like one example, and many similar examples can come for that.
So to optimize, let's say, hydraulic circuits.
Yes, to
and
yeah, to
processes.
optimize the quality parameters, actually.
Thank you.
More questions?
Hello, Mecit. Good to
Hi,
meet you.
Manuel.
Yes, very nice and interesting presentation. So, are you means I remember working with a company where they were developing the biscuits, cookies. I think that was also from Istanbul, if I remember. And but we use the relaxometry actually
Mhm.
for doing some quality check. Are you working with some companies already here, or any potential,
Well, for
partners?
that, no. I mean, this is like, as I said, we particularly worked on this emulsion,
I see.
gelation emulsions. Yeah.
Right, right, right. Very interesting, actually. What do you think that the speed of this whole process is? Do you think that it is a industry applicable in the sense like if we really look from the applied science point of view, do you think that industry will adopt?
Well, we can really obtain the results very quick. So, like if you think about a conventional rheological experiment, you take the sample, you precondition the sample, you operate the rheometer. So compared to that, it's super simple. Esma, how long was one measurement taking?
If the flow is obtained in a continuous way, if you obtain the laminar flow already, just depending on the sample T1, it can take 2 minutes,
Okay.
maybe, not more than this.
Okay.
So that is why it was super convenient.
So, sorry, maybe I'm asking futuristic question, or maybe you, I don't know. So, do you think that industry would accept the magnet placed in their processing industry, you know, and how do you see that that we can automate it completely moving forward? And also importantly, like, are there any certification that means, I don't know if you have talked to any potential user or like early adopter, for example, in this case.
Well, we haven't, I mean, I haven't, to be honest, thought for like that perspective, but first of all, I mean, yeah, this is a benchtop small magnet, so I don't think it will be problem to integrate it. And usually, whenever I'm talking about NMR to companies, I always say that, okay, you are going to use it for rheology, but at the same time, with static measurements, you can measure T1, T2. I mean, you can relate it with many other parameters. So this will not be just like a rheometer that you will get benefits. So it is compiling many other instruments which normally you use for quality purposes. So that can be a good marketing strategy to convince the industry.
So the cost of rheometer is also in the same range of 30 to 40,000 euros, right?
Yes, it is, but you need to also buy separate probes.
I see.
So that is like that might also be costly, and you need to to have this temperature control unit as well.
Thank you, Mecit. Thank you.
And one other thing, not all rheometers, for instance, can do your measurements at these low flow rates, at low shear rates. So for instance, if you are also interested in mimicking the oral rheology, so
Right.
that might for these shear rates, that will also be a very nice instrument.
Yes, yes, indeed, of course. Yes. Thank you, Mecit. Yeah.
So I remember just on the other side, maybe you cannot see me now. So just a question based on the thing which you have already shared, and maybe a little bit related to what Malak said. But the question is just simple. You talked about
Anuta, can you mute your mic? Sorry.
Sorry, is it okay?
We couldn't hear you well.
Okay. Huh?
Yeah, we can't hear you.
You have to switch off one, maybe.
Switch off what?
The mic. No. Okay, so at the end of your presentation, you said about obesity kind of application. And this is one of the hot topics all around the world. Just to understand this aspect a little bit, have you talked or have you tested or something related to this application? Or maybe you can explain this a little bit more just for my understanding.
Sure.
Because this is a really important issue.
Yeah. Okay. So the idea is here, for instance, what we did, I mean, I didn't go into the food chemistry side a lot, but this was PhD thesis of my student. We designed special emulsions called Pickering emulsions, which the hydrocolloids act as emulsifiers. So when you prepare an emulsion by using these Pickering particles, so you don't use any other surfactant, so you basically design an emulsion. These emulsions are stable and they have the ability to gel at gastric conditions. And our paper will soon be published in Food Hydrocolloids, so you will see the details of which hydrocolloid combinations we have. So what happens is at low pH, the polymers conformation change. and they form a gel. So, of course, this emulsion itself cannot be used alone. Like while you are designing a beverage, you need to integrate this emulsion, okay, with other ingredients. And you use this emulsion-based beverage, and when you drink it, so that it will gel in your stomach and it will make you feel full. So, and since we have this rheology change in the stomach, we wanted to monitor this change with this flow system. Okay? All right.
Hocam, actually, I have the image for the gelated emulsion. If you want, I can share.
Yeah, that will
to
be
see
good.
them.
Yeah, that
Let
will be good, Esma. You can share it.
Can you see it now?
Almost, I guess. Yes, we almost see. Yeah, okay.
Here is the cloudy gelated emulsions that you can see. We can determine the behavior of these. On the left-hand side, we can see the more particulated particles that we see the asymmetric velocity profile. The other one is more like a general gelation, network creating gelation type, and we see the plug flow for this type of emulsions.
Yeah.
That you can imagine maybe the situation. This is
And yeah.
Sorry. Yes,
Okay.
hocam.
No. Esma brought out a very good point. For instance, this particulate ones, also when you do it in a conventional rheology, the error rates are also quite high when you have such particulated. But with flow imaging, when you obtain a profile, it can be easier to obtain the rheological constants.
Yes, hocam.
Thank you, Esma. Yeah, your microphone, Danuta.
Johnny, Ingram.
It's fine.
Hello, everyone.
Hi,
Hello,
Pedro.
Danuta. Good morning.
Thank you, Mecit, very much.
Message, can I ask you
Really,
a question?
Sure, yeah, Pedro.
Pedro has questions.
Hello. Message, I just came up at the very end, but you just mentioned this possibility to gellify the mixture that you eat and then you produce the gel inside your stomach. Is there
Yes.
a danger of stopping your digestion?
No, that just slows down. I mean, there has been hypothesis on that. That just slows down the flow from stomach to your intestine, which is usually the criteria like how quick you will feel hungry.
Yeah, of course. I
That
understand.
was the idea. So-
The idea, I understand. I understand. My question was more related with the fine tuning of, making so slow that your digestion stops entirely, and then I mean, when that happens to me, I vomit. Okay. So you guess where this goes, you know? So,
Well, the thing is, it is not that possible because we have also seen that, for instance, if it stays too much after the gelation, the emulsion can have also like the protein, especially when you prepare it with the proteins, proteases start to degrade the protein, so you again have thinning of the fluid. So depending on which hydrocolloid you use, if you use completely indigestible fibers, of course you need to be careful about the amount you are going to eat. Otherwise, yeah, it will be too fiber, it can cause vomiting problems in your intestine. However, here we hypothesize that you're going to add this like to a beverage, like a kefir-like beverage, which will be slowing down in an extent. Okay? Yes, Danuta.
More questions? Well, it seems there's no more questions, so thank you again.
Thank you,
And I'm
Danuta.
wondering, Pedro, if you are here, maybe you could start. Because theoretically we have 5 minutes, but
Okay, yeah, I can start, and I have no problem with that.
okay,
I
please.
okay, I have to apologize for not being present so much in this workshop, but it's the right time for my classes, and I'm full with them. And therefore yeah, that's it. So I could not make it in another way. And I'm sorry for not being able to be present in person in Italy. And even here, I'm going to make a presentation, which is just eventually a starting point for any other discussion that you might want to have regarding data analysis. I didn't make any special preparation for this, and even the title I gave it is just to go around this FITEA software that is around and people use to fit data. So please be free to interrupt or ask anything. And during this process, actually, I will use some of the slides that I already presented in Paris in another workshop. And if you don't mind, I didn't change the slides, and you will see this. So if I'm able to share the screen. Okay. Okay, so if I'm not wrong, the title of the presentation is, if you remind me, I should remember. Okay, so let me find a page. Okay, so. Okay, so FITEA ecosystem, I don't know, the rest of it is features and something else. I'm sorry about this. And it's all around this FITEA thing. Okay, so the first thing I must tell you is that the FITEA is an idea, actually, is started by a need that I was facing when I was asked to analyze data from other people or provide or help to give to provide help to others when they were analyzing their data, and eventually give them or help them to install the software I developed for my own use during my PhD thesis. And during a lot of time, I was trying to keep up with the developments on compilers, operating systems, and it was becoming more and more painful to keep up with all the developments going around in the community. So I could no longer keep up the pace, and so I started to wonder if I couldn't make a web interface that would allow me to access, not only me, but others, to access the software and fit the data. And that's the idea behind FITEA. Actually, right now, I'm quite happy to see, not because it's just because it's a fortunate coincidence, but I noticed that now also Stellar, and you, Gianni, you might confirm that. I know that Eduardo is there, I think, in the audience. Hello, Eduardo. He can confirm that. So I think that you are moving on to this approach. So even your NMR console now is, I think, based on a web, uses this web-based concept where you have a browser that interacts or that allows you to monitor, control your relaxometer. So the idea somehow is now being used or is becoming, a practical solution, not only for, academical purposes, as for FITEA when it started, but now I see that you at Stellar are using it as a commercial product. So that's the idea behind FITEA. So FITEA is basically as basically a core which runs and makes the minimization and all the numerical number crunching and all that to produce the best possible fit, or to help you to get the best, to produce the best fit to your model, and provides a web interface. The web interface was made in 2009 or 2010, so it's quite some time ago. So it's looks outdated for many, users, and most people complain about how awkward it is. And it does not have all these goodies that you can introduce in modern web interfaces. But well, on the other hand, is very light and it runs and it works for all machines across. I mean, even a mobile phone or whatever device you have, you can access to it, and that makes the maintenance easy for me, since I have been quite, a little bit alone on this development of this thing. So, well, Fiteia, this is not, I think you are able to see this now. So, Fiteia is, has quite some some users across the world. I don't monitor this in a regular basis, but last year, and this is, this year in March or April, I produced this plot, and you see on the previous year there was quite a number of accesses and users from across the world. Most of them are concentrated in Europe and in the United States, but they, once in a while there are users from other countries accessing Fiteia. So somehow, to some extent, they find this platform useful. So where is the browser? Wait. Okay. So the browser itself has, the Fiteia server is a collection, actually, of smaller programs, modules, I would say, that provide, that help the user to do different things. The interface that you see here in my browser, that you can also access by typing in your URL fiteia.org or .com, is exactly this site. And this site is made with using this site's Google.com. So I'm using this Google infrastructure to produce this layout of this interface. So this is the front end that you might have. Probably well, let me just describe here briefly this page, so you have, a little bit about what I mean about us is that I've been a kind, myself being more actively developing this, but there's a couple of colleagues that also have been collaborating. So there's a getting started, there's a register, and there's a login. And there's some pages here related with the support. And since I mentioned the Fiteia ecosystem, there's a group of users that of Fiteia, which are the users in NMR community, NMRD community. And for those, I just created here, a branch of this on this platform for NMR relaxometry. And in particular for NMR relaxometry, I thought that it would be useful for new users to have a kind of NMRDpedia, which was the best name I came up at that time. And this site is an independent site, and it is intended to be a collaborative project where people could contribute with models and the basic explanations on how to use them. I don't maintain, well, it has been a while since I last updated this, But well, from time to time, I updated it. And I mean, I can tell you that the most recent update was this magnetic nanoparticles models that Danuta needed, or a student from Danuta, Alexander, that was visiting us. It was necessary to test this model. And so I included it in the library. So this was the last update here in this NMRDpedia. But the idea, I think, still holds, even if it's not, you know, is not growing with a steady growth. But I think the idea still holds. But I don't know how it will be in the future. If you'll stay here as it is, if you'll grow, or if you will vanish. Well, for the time being, it is like this. So we have this information. There is additional information about SPI, the documentations, a FAQ, you know, some tricks, etc. But let's say that we will just want to have a go and try the platform. Fitea being a service on a remote server, it means two things. It means that the user does not have to install software in his own computer, which in my opinion is an advantage to a certain point. The disadvantage might be that the data will be transferred to a remote server where the fit will be made. And if the server is not working, then the user cannot you know, do anything. And also there's a possibility that the server is not running, or for this, there's a problem, a technical problem, and then the solution might take some time, and then the user might not have access to his data. So it's I didn't want to have that. So I keep two machines running in two different sites. So both the hardware and software, they run in different places in Lisbon. And so, well, there's a chance that at least one of these servers is running at any given time. I keep an eye on them and I try to keep them working all the time. So for a new user, you can register or you can log in. Here I will not show you how to log in, how to register. I think you can try for yourself if you didn't do it before. Muhammad is here in the audience and is preparing a playlist of videos, tutorials that were originally made by Maria Beira, a former PhD student of mine. And Muhammad is doing the translation for English. He's producing the English version and actually the Urdu version. I believe that he will do that also for his own language in Pakistan. So there will be 3 playlists of these videos in Portuguese, English, and Urdu in the near future. Anyway, so we can log in. Well, the user is asked to provide a valid email, and then if the registration process went through without problems, the layout of the page changes and the list of folders appears. And these folders are the working folders of the user. So if you are a new user, most likely you don't have as many folders as I have here. You will have probably just 2, the tutorial 1 and another one, which is the tutorial NMR, which is here, tutorial NMR. So you will find in your account this tutorial 1 and tutorial 1 and tutorial NMR, the 2 folders that exist all the time by default. And even if you delete them, they will appear the next time you log in. So they are always present in the system. And so this is the first page. So when you click on one, then you are immediately directed to one of the modules of Fitea, which is devoted for fitting. So I call it fitter, which you might see here on the top left of the page, there is Fitea Fitter 1.1.0. And this is the fitter module. But if you notice here on the right side of the browser, you will notice several links. Well, besides the help, which is, I think, self-explanatory, you have basic, advanced, expert, and master, and these links only define or set up some defaults that help you to deal with problems with different degrees of with different complexity levels. Then you have a calculator module, a plotter module, a report editor, and then some tools to upload fitting projects that you might receive by email or might have been shared by you by someone else. You can always return back to the page that you saw before by clicking on My Fits. So that's the way to go back. So this is the fitter module. The basic, advanced, and expert modes, as I said, they help the user to deal with different problems with different complexity. The master mode, which was the last one being developed or integrated in the system, is becoming a kind of standard these days, because actually in the master mode you can do basic things as you do in the basic mode, and advanced and expert things as you would do in these advanced and expert modes, and you don't have to change modes to move from a simple thing to a more complex thing. So master might become the default, the new default in the future. I don't know. Maybe it stays like this. So when it comes to fitting, and I'm sure that all of you must have done some fittings, some data fitting in the past, and I'm sure that you will agree that in the end, you need you need to have a place where you put your data set or data sets. You have to define the plots, how the plots will be, define the scales and all that. That depends on the software, of course, because in, like Origin, in Origin, you just select the data set that you want to plot, and then you click somewhere in a button and it produces a plot using some defaults predefined by the system. And then you can optimize or customize your plot by changing the parameters of that plot. But the plot parameters have to be set somewhere in the system, and I'm sure that you have tuned them or customized them at a given moment when you are dealing with your data. And if we are actually doing a fit, then we need obviously to set a fitting function. And the fitting function, how it is written, and how it is written and how it will work, it changes from software to software. But here in Fitea, the user is invited to write at first a single equation or expression in which he defines the independent variable and the dependent variable. I don't know if this, if this is too small, the fonts are too small for you to see, or are they okay? Are you able to see this in a good manner or not?
Yeah, they are okay.
Yeah? Okay. So, if you, well, but in any case, I can increase it. Okay, so here I just wrote an expression which is a plus b times x. So it's a straight line, is a linear function. I could change here and I could put c times x, and that will make this a parabola. Or I could say, I could make x comma 2.0, and I would be using the POW function that in C will make possible to have a power of 2 of variable x. If I do that, I mean, I'm including a new parameter C, so I will have to declare it here. So these are common features in all software somehow to some extent. The interesting thing here about Fitea, but is also a common feature in most software packages, Origin, for instance, has this possibility also, is that there might be a library in the system that provides or help the user to save time instead of writing a full expression here that might be quite complex. It might be easier to select some functions from a specific functions library. And that brings us back to the NMRDpedia, for instance, you know, I have other functions for other purposes here. You know, I have Lorentzians, Gaussian curves, elliptic integral, Jacobi integrals. This is for the benefit of students here at the graduation level, where they have the Biot-Savart law for to calculate the magnetic field generated by coils. And so there is a kind of library here already prepared with some models. And of course, in the NMRDpedia, you will find, as you might have seen here, relaxation models for several types or classes of molecular motions, like rotations, reorientations, translation, self-diffusion, collective modes, as those found in liquid crystals, paramagnetic relaxation enhancement, cross relaxation, relaxation in confined systems, polymers, and others. So the user can select one of these expressions, just copy it, and come back to the function and say, well, here I'm using a constant and I'm fitting a constant plus a BPP in this case. Okay. By the way, in the NMRDPD, if the user wants to know what the BPP is, then a text was introduced here, and there you have an introduction, and then you have some explanation how to use it, the units. You even have a kind of not the full version of the code, but the simplest code you have. In this case, for the BPP, there is also Octave and MATLAB versions for this code. So there is some information that the users might find valuable to understand what they are doing. But anyway, this is how we can write a function and put it here. Okay, so I'm in tutorial NMR, so for instance, I can say, and I can open, or I can, let's say, write and create a new fitting by using the equations here, like P times X times C times X times X, not here is plus, and after compiling, there is a new layout. The new layout, together with compile without errors, is a sign that everything went through okay, and we are ready to fit. And this is now this drop-down button has two options, global or individual, and this is a feature of this master mode, which allows us to either play with the fitting interface at a basic level or at an advanced and expert level. So let's say, I would say the basic level is when I'm looking and I'm preparing to do an individual fit. Well, if I have only a data set here, in either individual or global, has no, there is no difference. But I didn't explain before, but I can here create more than one data set. Let's say this is 2 and this is tag 2, and I have a different numbers here. I can put 2, 5, just to make them different. 3, 1. So I can data plot. You see, I have two data sets. I see only one plot, but I have here a possibility to select from these blocks which ones I'm going to see. And now I select 1 and 2. And if I data plot, I will see both of them. Okay, so you see, I have two data sets, and if I choose to make an individual fit, it will fit these two data sets independently of each other. Okay, I'm fitting a parabola to both data sets, and the parabola is obviously different because the data sets are completely different. So this is the type of thing that you do when you play with in the interface. But this is and you can create folders here by setting a folder name here. You can give a name to this particular problem that you are fitting. This is file name. You can choose one, and it will be saved in this folder name. So this is the place where you define new folders for your problems. Once they are overwritten or archived, I can explain that, but you probably will find that easily by yourself. Once you do that, once you save this project and you saved it in a kind of more permanent way, because I must tell you that everything that I'm doing here will vanish. It's just if I close the browser, if I go away. There is no memory of this. This is stored in the system. You can use it when you are logged in the system, when your system is on. But if you close it, if you log out, eventually this information will be lost. So the way to preserve the information is to either overwrite or archive this information in a file with a file name in a folder which you define. And once it is saved, you will be able to see it here. So the BPP model was a fit I made, which I gave it the name BPP model. So instead of file name, it was BPP model, and I just click on overwrite, and it create me this entry here. I have many here, as you can see. One is the BPP model, and then I can, in a different day, in a different occasion, I can recover it. And you will recover what you saved, basically the data that is here. The model that you see now back down here is written, is a BPP plus or nothing, just BPP. Yeah, it's just a BPP model. You will see it's not a BPP as you might have, remember seeing just a moment ago, because inside this is one argument of the function BPP. So I can make calculations in the place where there would be an argument in this function. So, but this is typical of a programming language, so there is nothing special about this feature. But anyway, this is a BPP. And we can detail and check what this is, but this is the tupular coupling constant as defined, and this is the definition of the spectral density in some way. Actually, it's the prefactor of your BPP, which is defined there. And the parameters are stated here, are declared here, and when you compile, you get the table with them. Some of these parameters are actually constant, like the gyromagnetic ratio for protons, the h bar, so the Planck constant divided by 2 pi is defined here, the value of the spin of your nuclei, which is 0.5, which is 0.5, and then you are left in this model with two parameters. One is the correlation time, the other one is the interproton distance in your system. And this eventually might be the two independent parameters, and when you fit, you will get eventually the best fit you can get. Here you have again the question of global versus individual. Since there is only one, both will produce the same thing, but I can, for the sake of clarity, use individual. And if I click fit, I will get the fit. Or not. For a reason I don't know, to be honest. Oh, okay. Yeah. There is an error. No problem. I can detail the error, but yeah, it's a possibility to. Okay, so let me explain the error. Although you might find it is strange. Anyway, I have the expression declared as z is equal to something, so the dependent variable is z. And as you might see, I have here first independent variable and a second independent variable, which is dum as a name. Actually, this dum, or the name of this second independent variable, should be the same as it is here in this particular tag. This is a hash tag data, and this is a hashtag tag. And this is the two special lines that help us to separate blocks of data. So this is a block of data. And if I copy and I make here, I create a second block of data. This will be the second block of data. And if this would be a temperature, this could be another temperature. But since I declare the second independent variable as dum, this instead of y, I should have dum. Or vice versa. I could keep y here and I could put y here. Okay? Let's compile again and try again. This time, the fit finished. I have a chi-square and I have some uncertainty for my parameters. But I have to be cautious about this. Let me just remove this because I don't want to make things complicated. So I have just a fit, the data set I'm fitting, and this is simulated data, okay? And I got two numbers. And below the plot, I have several links which provide the user with additional information. This is a log file which register all the actions made during the minimization process. And the most informative part is the log of the MinWi routine, which is the chi-square minimization routine from the CERN library that is used by the system and produces useful information. For instance, when the scan minimization method is used, the chi-square, which is here the vertical scale, is plotted against the value of each independent variable, which in this case is r. And we expect to have a minimum, and indeed we have a minimum, and there's a minimum of the chi-square for a given value of r. And the same thing happens for tau. So I can, or the user can check here if the minimization occurred nicely or something awkward happened. So there is additional information below and above, and I will not detail it here, but you can have it there. And then there is a couple of links that provides additional information. One of them that is useful is this curves. Curves is a link that will help you to download the values of the fitting curves. So this black line here, you can get it from these curves. So if I type on curves, you will try to download a file. I will say, okay, and I can open that file. And it's a file which is basically a table which contains in this case, the first column is the frequency. The last column is the total relaxation rate in this case. And in between the two of them is the components that produce the total relaxation rate. The possibility to draw or to see the components of a relaxation model is it's a very nice feature. It's a very nice feature. Let me see, or let me show you another example. This is an example prepared with the data provided by Stellar, by Gianni, some time ago, as a kind of calibration data set. So I can recover this. This is manganese chloride solution, water solution. And you see you have a dispersion. These times the scales are different. And of course, the model here is different because we are now dealing with some paramagnetic relaxation enhancement in addition to the relaxation of plain water. So the number of fitting parameters is larger, or the number of parameters that we have to worry about or to set is different. But basically, from the point of view of the fitting, everything happens as I showed you before. So when I click on fit, I expect to see a fitting curve. But this time, as you see, besides the black curve, which is the total relaxation rate, which is actually the values that we are comparing with the experimental points to fit the data, we see some dashed lines in color, here one in red, another in blue, which are the components that I'm including here in the relaxation model. So let me put some spaces and make it larger for you to see. So equal to, this is one contribution, and this is another contribution, and that one is another contribution. So I have three contributions here. I can tell you what this backslash is in a moment. So you have plus, plus, so we have 1, 2, 3 contributions, one of which is just a constant. Where is this constant, by the way? The constant here is barely seen, is this green curve here that you see very close to zero, because it's the relaxation rate of water in this linear scale is very close to zero. In order for me to see it, or for us to see it, I would say I would just have to change from a normal scale to a logarithmic scale, like I'm doing here. Also make a copy here and put it here, and here put 9, and I think I can have a go and either fit or plot. Fit recalculates and tries to get a better, a new set of fitting parameters to produce an even better fit. So you can fit over and over, try to improve your previous fit, or plot, which just draws the fitting curves or the model curves for these parameters exactly that you are on the table. So this time I will choose plot. So you see now clearly there are three components, the green, the blue, and the red, and the three of them combined produces the black. So this is an important feature, and software that does not have this feature, most of the time it is not helpful for the user, especially in case of fitting complex data sets with different contributions, because the user benefits from knowing which model contributes more and in which frequency each model contributes or makes its more important contribution. And this can only be achieved if the user has the possibility to see the components independently. So this is an important feature that I should stress, and the users, I invite you to find or look for it in other software packages, because they should implement it, in my opinion, in my view. Okay, so there's additional links down here below the plot, one of which is this PDF report, which is just actually a PDF which you can download, and then I can show you if I can. Where is it? Here. So PDF report. So it produces a PDF report. So a report of your fitting with a table with your parameters and something that you can just, send someone just to show that you did the fit and the quality of the fit and some features of it. So this you can do. Actually, the PDF report is based in another module of this FITEA ecosystem because there is a report editor here, report editor. And this report editor is basically an interface to a LaTeX compiler. So the user, is automatically done when you click on the PDF report link. But the user can type things here, and I just trashed that. I'm just put some garbage characters there, and can compile and PDF LaTeX and produce a report, which now has some garbage here, some nonsense text that I put it here. So this is another module that is present on FITEA. Eventually, if the user wants to customize the PDF report that is being produced by the system. Okay, so this is more or less things that you can do with FITEA. Obviously, in the tutorial model, you have other examples, and if you ever go and log in, you might explore them and see different things. I showed you these things that are in the tutorial NMR, but in the tutorial 1, you have a different set of examples. Let me try this basic 3. I don't remember what this basic 3 is. It's not very interesting, perhaps. Maybe this one. Yeah. Oh, this is, for instance, an NMR spectra that I'm fitting with a sum of Gaussian curves. And by the way, this backslash that I mentioned a moment ago, this backslash is explained here below what is its purpose. But basically, it allows the user to decide to show or not the independent components that or the terms that combine produce the total value of the function that is being fitted. So y is a plus a Gaussian with a backslash a and the Gaussian are shown as independent curves. If I remove the backslash, they are combined together and I see a single line. But here, in the case of this spectra, I think you will see the advantage of identifying the independent curves, because you see here the green, the yellow, the purple, the red, and the black. It's important. It's an important thing to see these independent components and how if we combine them, how they produce the final realization rate. So here it's easy to see that if I'm concerned with the green curve, and where is the green curve? The green curve is here. So I see here in following the order is the second curve. So the first is red, the second is green. So the first is an A, the second is the green. So that would be the second function here. So I know the parameters that influence the second function. So I can come here and the second function is there. For instance, I can maybe change here slightly 2, and if I want to see the effect of changing this number here, I can simulate the curve by clicking on plot, and I see the effect that produces the change in this parameter. So I see the green curve being shifted to both sides. So it's important to know where each parameter produces its influence in the fitting. So this is important knowledge. Okay, so this is the FITEA as it is, as it runs presently. The information that is being actually stored and is relevant for sharing, for instance, it's actually 2 or 3 files that you have to be concerned about. You can check them in this using these browse links. And if I click on this browse, you will see you just browsing the files and see the contents of the folders that are associated with your account. And there is one folder in this, which is the fit folder. And once you go there, you will see also a list of files. But the ones I want you to pay attention are the ones that have this extension, SAV, or the functions PLT. So the SAV functions are the functions that contain the information for the fits. The PLT are informations that contain information for plots. This is probably the time for me to mention these plots. What is this plot? I forgot to tell you. Okay, so I was speaking about the modules that are combined in the Fitea ecosystem, and one of them is Plotter. Let me click on Plotter. Plotter is a different environment. Plotter is just entirely devoted to just make the plots and to help the user to make a little bit more complex plots than the plots that you see in the Fitter module. Is not as advanced as Origin, for sure, and you will find many features are missing here, but still it can be it can make interesting things with it. One of which is to import the plot that was previously done in the Fitter module. So I can import this fit graph 1, which was the last, is the plot that was last produced in the Fitter module. So I can import it, and you see that is the plot that we saw previously in the Fitter module. And here, all the data that is being shown in the plot are here shown in separated boxes. And each box, you can set the line types, the symbols, the labels, the strings, etc., etc. And so you can customize and tune your plot in the way you want. So this is the plot. And as for the fits, you can define folders where you save them. You can define the names that you will give to them. And as for the fitter, you can select and recover, and you can also download. And that's where now I'm moving on to the next step, or to the next feature, or to the next thing in this Fitea ecosystem. Okay, so save and PLT, SAV and PLT. So these are the plots or the files that are worth saving. You can download them. Let me see example. So this manganese chloride data set, I can download the file. If I download the file, or if you download such a file, you will see that the file itself is a text file. Oh, I have to choose the, where is open with text. Okay, so the file itself is a text file. It's defined in this format where you have a key and a value for that key, and it's a list of keys and values. Some of the keys, like dados, sorry for the Portuguese, it's data, and there is a long list of characters that contain the data. As well as scales and even the function. For instance, the function here, like say keyword function, and is the definition of function. You notice that many of these characters look awkward because they are HTML characters, and so this file is not very interesting from the point of view of reading it. But it brings us now to the next thing, which is it possible to use Fitea without using this web interface? And the answer right now is yes, after the efforts that myself, Eduardo as well, I have to thank his contribution, Muhammad as well, Lionel, we have been working in a kind of the fitting engine and the possibility to have different interfaces for this fitting core that is behind Fitea. And this now is available. I will try to have GitHub here. I don't know if it's here. So you will find the software at GitHub. There is a GitHub/Fitea that you can have access. And here, one of this, there are two actually areas, two regions, two areas, two packages. One is the OneFit engine and the OneFit engine APIs. So APIs is just application interfaces. So are interfaces to play with the fitting engine. And this software or the software in these packages can be downloaded and installed in your computer. The fitting engine is, is still undergoing tests. Actually, right now, I don't know when was the last time I updated. I mean, I have several updates here. So 2 months ago. So my last update was from July. I didn't do much in August and now in September, but I was heavily involved in this before that. So you have installation instructions. If you are a Windows user, I advise you to use the Windows subsystem Linux and follow these instructions to install it. If you are a Mac user, you can install it in a kind of Mac OS native, or if you want to have virtual machines, you can use Colimar and Docker, but you have several options here how to install it. Eduardo, I don't know if you are there. Sorry if I don't know if you gave a talk or not.
Oh yeah, I already have a talk 2 days ago. But yeah.
You gave a talk and you probably mentioned some of these things. I don't know how much you mentioned, but
Yeah, I mentioned the fact that in our software right now we are using OneFit engine, that is this core
okay,
engine that you provide, and it's nowadays like integrated.
okay.
And we are
I'm
able
sorry.
to do that.
I'm sorry for not attending your talk. I mean, I missed it because I'm sure that you showed the new features that you have probably polished in your last versions. But if you can spare some moments afterwards, you might, give me a private talk just to update me with the new features. But just to tell you then that this fitting engine now is available and people can download it, install it in their own computers, and then develop their own interfaces for it. My advice is, not advice, but my thing, I mean, my perspective is the following. If you are going to analyze data in a regular basis, and if the data you are going to analyze is more or less always of the same type, then having a fitting engine in your local computer with some either graphical or text-based interface might optimize and automatize your data analysis and data fitting. And then you can really benefit from the fitting engine and from not having or not spending so much time uploading data to a fitting package like Fitea or something else, and dealing with all these clicks and choices and tests and customization that you have to do every time or pretty much every time you fit a new data set. So if you are dealing with a regular analysis of data, more or less of the same type, then you can benefit from, you can invest time in preparing a tool based on fitting engine can be helpful. Of course, there is always the possibility that you are interested in developing a full graphical interface to have benefit for the full features. I think Eduardo is introducing some features at the beginning just for the magnetization decay, but he's aiming as well to fit the dispersion profiles. I don't know how much of this is already, if you tried already to do that or if it's ongoing. But once you go that way, then you are moving on to a kind of FITEA kind of thing in what concerns the analyzing data from NMRD profiles. Actually, there is no big difference in fitting NMRD profiles or any other data. It's just the choice of functions and the particular defaults in your plots, in your graphical presentation, because different data or different types of data require different ranges, different settings to have a, to show the data clearly. And that depends on the problem. But once you have an interface to deal with the fitting engine, you will be able to fit any type of data or deal with any type of data. So there is no big difference. Only or eventually, it will depend more on the functions or on the liberty or on the freedom the user will have to write down their own fitting functions, and the number of functions that are included in the library, included in that particular, fitting toolbox. That will define the extent of the use of that fitting engine. So fitting engine is there. The APIs here are just testing APIs. Probably the one that is more maybe interesting for new users that might have a go, especially if you are dealing with the stellar output results and you don't have the most recent NMR console, which might also already include the fitting engine, is this Muhammad API in Python, which helps you to analyze the SDF or HDF5 files that are produced, that are saved after a fast field cycling experiment, and that you can post-process the magnetization decays using this interface and using the fitting engine. Yes, I included here also this additional JavaScript-based program, which tries to produce a new web interface for FITEA. This was made by a student, a physics student here at the university, and he gave the name FITEA 2.0. It's you can have them running eventually if you install that. I'm not sure that, just a second, if I'm able to show it to you, just to give you an idea. Yeah, I think I can try. Yeah, okay, it still runs. Okay, so this would be FITEA 2.0, so it would be a new interface with all the or most of the goodies that Eduardo knows well about, these fancy graphical things for in web design. Maybe not as elaborated as you have them in your console, in the console you are designing, but nevertheless in the same line. So it's a question of optimizing this web interface. Unfortunately, she's not working any longer on this, so this stays there as an example for people to check. Well, I could go on and on, but now it will be just specific things and details about this. So about the ecosystem, and the features, I'm pretty done with it. So you are welcome to ask me any questions. If I will try to answer them. I'm sorry, I didn't provide any examples of advanced fitting using Fitea. I can provide those examples to you, or I can show them if you really want me to do it. Okay. So thank you very much for your attention.
Thank you very much, Pedro. And those of you who see Vita for the first time probably are surprised in a very positive sense regarding the potential of this tool. Suppose many of you already saw and admired it. Questions. We need questions and we have time to answer them. I mean, yeah, Pedro will be answering them, but it's some time for questions.
Hello, Pedro. So if I may
Hello.
ask,
Yes.
thank you for the in detail presentation. So I have you presented like there are a number of users from different countries. They downloaded the software,
Yeah. Yes.
and I was wondering, do you have any insight on for what they have downloaded and for what they use this software?
Yeah, I can try. If you spare me a few seconds for me just to locate the information, just a second.
Sure.
Because it has been a while since I tried to see it. So it's a good opportunity to do it together with you.
Okay.
Let me try to show it to you. Okay, let me try here. So, no, here. No, so not here. So, no. It is. No, but I don't want that. Actually, it's not analytics. Analytics is a different thing. Sorry, my confusion now. Analytics is a different thing. No, one second. Second. So it's Google. Okay, Google. So Google Drive and user. Yeah, not this one. User. Fitea survey. Yeah. Okay, so there is a survey available in Fitea. So when you log in, login page. Okay. There is a Fitea survey. People are invited to give some feedback. And now I'm lost. Okay. So not many people responded. You see 401 responses.
Yeah.
Well, it is as it is, but there is a couple of things. So you can see, I mean, most people are undergraduate students. Okay, it is used a lot by students at university here in Lisbon and in United States as well. In several universities in the United States, they use it. Most of them is academic, okay, but some people in the industry as well, and some as research. So you see, then most people are recent users. So definitely there is a number of people that use it when they are doing the courses here at university, and they stop using it, or they use it on occasion, on a daily basis or on a weekly or monthly. So there is a thing. Then the opinion versus of this being commercial versus non-commercial, you see, people like the fact that it's non-portable, open source, etc. The things that new guys, I mean, recent people like. Then there is the question of the basic, advanced, and expert and master modules, where people would expect to have interfaces or improvements. Yeah, so this is it. So then some comments at the end. So I'm showing you the feedback that I'm getting from the users on a kind of non-regular basis, in a volunteer basis. So
Right.
to be honest, being me alone keeping this, I don't have much time to address the the wishes of the users in one particular direction or another, right?
Yes.
The only thing I did to address the wishes of the users was stripping out the fitting engine from the Fitea and make it available so that, for instance, Eduardo and you to incorporate it in the console, and also for us to bring it closer to our own console downstairs in the lab, as Eduardo knows. But also, I realized that also my former PhD student, Maria Beira, she's working for a company that looks in the hydrogen energy cycle. So production, storage, generation, hydrogen generation, etc., fuel cells. And they also need to analyze data in a regular basis, in a kind of automatic basis. So the fitting engine might provide some, avoid the overhead work of getting a practical, useful fitting system with advanced features included. Because to write a program to make a fit of a linear data set is easy. You can ask ChatGPT, it will write you a software for it. Okay, it's no big deal. For a parabola, it's the same. You can do it, but then if you want to have a general purpose with some flexibility, if you want to write your own library of functions, if you want to reuse the software in a different context, then immediately you stop and you need to move on to more advanced languages or development platforms. And things like Python and all the numerical libraries available in Python, or even Origin, they also have their overhead work. And when it comes to Python, some of the things are there, but then you have to play again and developing your own philosophy behind the fitting strategy. So what Fitea does and what the fitting engine has, and I apologize, but that's it, is my view of the fitting problem and how to address it in complex situations. Okay? It's certainly not the best, but is flexible enough to deal with all the problems that I faced so far, including the most complex thing I did was this COVID data analysis thing with the differential equations. And so if it is able to deal with that, I mean, I can deal with pretty much everything if you want. So that's what is in the fitting engine, right?
Yeah.
For fitting a straight line, you don't need it, okay? But if you have to fit a straight line and a multi-peak spectra or paramagnetic relaxation enhancement with magnetic nanoparticles together with polymers and something like that, then immediately you face a problem that you have to spend a lot of time developing your own software to do it, okay? Because it is as it is. And so in that case, it is helpful. So that is what goes along, or what is shipped in the fitting engine.
Yes. Thank you, Pedro.
Yeah. More questions? Pedro, is the number of the users increasing? I suppose so,
Number of
but
users.
how fast?
Ah,
When we talk about derivative.
Yeah, let me. That was the analytics part that I was here trying to get. Okay, so last 30 days. Okay, last 30 days, I got 213 new users, or maybe not new users. I'm not sure if this number are new users, are active users. So, and 68 from the United States. I think I can. Few countries. Yeah, I can, I think, give.
I think there is this tab of new users.
Yeah, okay, so you see users, yes. Okay, so, yeah, okay, so here is a kind of thing. So I have 218 new users in the last 30 days, 94 in Portugal, in Lisbon, 13 in San Diego, a couple in Ireland, okay, so it changes, it grows every year, of course, but the users will not keep doing fits afterwards because they use it when they are in, at university in the courses, when they need to use it. It's not, this is not a social media thing where people keep coming just to, keep updated things. So they use it when they need to use it. So yeah, the number of users increases and some of them return in the future. My students here, they use it in the first year, second year, third year, and eventually when they go to master and PhD thesis, if they go abroad, they will keep coming and using it. And then they have PhD students and students, like say in New York. So they start to using in New York, in Columbus. But in San Diego, for instance, San Diego was something out of, nowhere. I have no. Once I got an email from a colleague from San Diego and said, well, I saw this, I want to use this. Can I use it? Of course. And then I want to fit a Poisson distribution to some data. Can you help me to that? And so from then, that moment on, they are using it. So, and as they use it and they go. So Danuta, yes, the number is increasing, but that doesn't mean that all of them keep using it all the time.
I have one question, maybe both from Pedro and Eduardo together. So the question is simple: how much of the FITIA which we just saw today we can integrate in our Storm 6? Like how much? And the other question is from Professor Pedro, that we are using FITIA here in our softwares, maybe using it daily or for new customers. Does this analytics also considers us as a user because we are using the OneFITIA engine, or it's just like your survey, or this Google Analytics takes only those who use OneFITIA as a like web-based software?
No. I mean, these analytics that you are seeing is just for FITEA. They are nothing. There is nothing in the fitting engine. Don't worry. No. This analytics just follows the access to the web pages on FITEA.
Okay.
Okay.